So we talked about the product rule, right? If you have independent choices, independent ways to choose, or independent choices that go into choosing something, and you can just multiply the number of choices. And in particular, I wanted to pick up with, I want to do a few more examples of that, and I wanted to pick up with the example that we ended with, and kind of think of some variants of this example. So we had this example where we've got 10 different kinds of soup, and you're going to eat one per day, and the total number of ways you could do that, we can use the product rule if we think about it in the right way, right? The first day we have 10 choices. The second day, we don't have 10 choices anymore, but we will have 9 left, whatever they are, and we can choose any one of them. So they are independent if we think in terms of choosing any one of the 9 that we have left. Anyway, the total is going to be this product, which we can write 10 factorial, right? So in general, n factorial is the number of permutations of n things, or the number of ways to put n things in order, right? And you should memorize that. I mean, if you use it enough, you'll remember it, but what you should remember is why that's the case, right? It's because of this argument that I have n choices for what to put first, and then n minus 1 choices for what to put second, and so on. Okay? So, looking up with that, what if, so, picking up the previous example with soup. What if, so, there's the same scenario, except I only want to eat soup for the next 4 days. So I only want to eat soup for the next 4 days. In other words, I still have 10 cans of soup. They're all different. But I'm only going to eat soup for the next 4 days, and then I'll have some soup left, but that doesn't matter. So the question is, how many different ways can I do that? How many different schedules can I make for myself for what soup I'm going to eat for the next 4 days? You don't think? How would you answer that?
Sure. If we know that for each 10 cans of soup and 10 days, it's 10 factorial, it would be the same if there were 6 days, what would be left over after it's done. 6 factorial, so 10 factorial minus 6 factorial.
So that's not the right answer, and I'm trying to think of how to explain why. I mean, I know it's not, but let me think for a second to explain why that's not correct. Yeah, subtracting doesn't really make sense because, like, the number of ways I have to eat the things that are left over doesn't really have anything to do with how many ways I have to eat for in the first place. Like, it's not like, there's a bunch of ways, but then, like, I can't use the ways that would correspond to eating the 6 left over, so I have to subtract them. Yeah, just like, I'm not. It still doesn't seem like a very satisfying explanation of why. If I think of a better explanation of that. Have you?
Would you divide them instead? 10 factorial divided by 6 factorial. So you just get 10 times 9 times 8 times 7.
Okay, so yes. So, I could use a similar argument as before. You say, well, the first day I have 10 choices. The second day I'm going to have 9 soups left, so I have 9 choices of what to get on the second day, then 8 choices, then 7 choices. But then I stop because I'm done. Right? So, 10 times 9 times 8 times 7. I don't know what that is. Doesn't matter what number it is. 10 choices on day 1, 9 on day 2, etc. And I think, as Matthew was saying, one way that we can think about this, or one way we can write this, right? If I say like 10 times 9 times 8 times 7 times 6 times dot 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 times 1, right? If I divide that by 6 times 5 times 1, right? So all these are going to cancel out. Even the ones cancel. Right? That would just leave me with this. That makes sense? So, but I can write this as 10 factorial divided by 6 factorial. And I think there's a way, if you wanted to, that you could kind of connect this to counting how many ways you have to eat the leftover soup and why does that mean you're dividing it. We're going to talk about division more later, and maybe we can come back to that. But for now, we can just say, well, we can understand it by just saying you do this same pattern, but you stop after 4 days. And kind of a convenient way to write that is just by saying, we're not necessarily saying it's connected to the 6 soup that's left over. We're just saying, yeah, a convenient way to say 10 times 9 times 8 times 7 is to say, well, it's 10 factorial, but then you cancel out 6 factorial, and you're just left with those first 4 things. More generally, right? Let's replace the numbers 10 and 4, right, with just variables, right? If I have n soups and want to make a schedule for k days, then I have, well, on the first day I have n choices. On the second day I have n minus 1 choices, and so on, right? N minus 2 choices on the third day, all the way to, how many choices do I have on the last day, on the 8th day? Well, if I actually went if I went n days, and I ate all the n soups, then I would have 1. But if I go, in general, if I go only k days, how many choices would I have on that last day?
N minus k.
No. I knew someone was going to say that, so thank you for falling into my trap. That's what you would think, but let's think carefully about what it is.
I mean, no, it just looks like n minus k plus 1.
Yeah, that's right. Think about, so here, it's helpful if you think about, let's put back another specific example for k. Let's say, okay, what if k is 4? Well, then I'd have n times n minus 1 times n minus 2 times n minus 3. That would be the first 4 things, right? So actually the last one wouldn't be n minus k. It would be n minus k plus 1. Which we can rewrite as, well, if I say n factorial, what do I need to divide by? I need to cancel out, well, the thing after this would be n minus k, and then n minus k minus 1, n minus k all the way down to 1. So I really need to cancel out n minus k factorial. write it in this form, then we don't have that annoying +1 in this thing. Okay, again, let me emphasize, do not memorize this formula. Right? You should understand how we got this formula, and then you can use the same reasoning either to rederive this formula if you need it, or you can apply the same reasoning to a slightly different situation and figure out what that is. Right? The problem with memorizing a bunch of formulas is that it's extremely inflexible. You can solve specific problems that specifically use that formula, but you can't solve similar problems that are slightly different. Okay. I guess we should specify that k has to be less than or equal to n. It doesn't really make sense if k is bigger than n, because then we would get like negative something factorial, which it also just doesn't make sense. If I have 10 soups, I can't make a schedule for 12 days because I'll run out of soup. Here's a good question for you. Does it still work? Does this formula we came up with still work even if k is equal to n? So if I say I have n soups and I actually want to make a schedule for n days, does the same formula work? See some nods, so there's quite a few words.
Well, in terms of the top part,
This part? Yeah.
yes, when you iterate all the way down to 10,
Right.
it'll be 1.
Yeah, and 10 minus 10 plus 1. Yeah. So you're right. So this part makes sense. But what about this? Does this formula make sense? Doesn't that make sense?
Yes, because n minus n is 0 and 0 factorial is 1.
Right. Yeah, n minus n here would be 0, and we would have n factorial divided by 0 factorial. So, and we've said before that 0 factorial is 1. You could also see this as some evidence that 0 factorial ought to be 1. Because if 0 factorial is anything else, this formula won't work. If 0 factorial is 1, then this formula works for any n of k, and that's nice. And that's why we define 0 factorial to be 1, is that there's lots of cases like this where it's like, if 0 factorial is 1, then everything works out nicely, and you don't need a special case. Because we can choose what 0 factorial means, right? I mean, we as a species, not like this class. Okay. Cool. So one more example I want to do about the product rule, and then we're going to move on to talk about some other principles. Given finite sets A and B, how many distinct functions from A to B are there? Okay, and I consider two functions are distinct if there's some input for which they give different outputs. So I mean, I could define that. That's just what you would assume, I think. So functions are distinct if there is some input for which they give different outputs. In other words, it doesn't matter if there's two functions that give the same output almost all the time, but then there's just like one particular input on which they give different outputs, they're different functions. They're similar, but they're different. So, maybe let's just do a small example. It's like a sub-example of the example. How about like bool to bool? How many bool to bool functions are there? There's like, so here's true, false, there's the function that just sends true to true and false to false. That's the identity function, right? What would be another function from bool to bool?
The one that gives true another one.
Okay, yeah, so there's another one that says, no matter what, it outputs true. Okay, any more?
The same but for false.
Okay, yep, there's the one that always outputs false no matter what. Any more? Oh, yeah.
True outputs to false and false outputs to true.
Yeah, so there's the not function, the negation function that swaps them. Okay, is that all of them, or are there more? I was willing to say. How many people think that's all of them? You're right. So in this example, there's 4 such functions. This is maybe a deliberately obscure example because there's 2 booleans, and there's lots of different ways you could combine the numbers 2 and 2 to get 4, and it's not necessarily clear what the right operation is. But maybe if we did a bigger example, it would be a little clearer, but it would take a while. So let's just think, if I in general, I've got, here's my set A, and I've got my set B, and I want to think about choosing a function. Remember, whenever we say, we're counting how many things there are, another way to think of it is, let's say I have to choose one, how would I do it? Well, to be a function, every element of A has to go to something in B, right? So really, what I have to choose is, for each element of A, I have to choose where it's going to go, right? And those are all independent, because, if I said, it has to be injective, or it has to be surjective or something, then they're not independent anymore. But if I just say it can be any old function, then it doesn't matter. Each element of A can go anywhere it wants, and it doesn't affect the other ones, right? So, maybe I could look at this one first, and I say, well, this one, I'm going to send it here. I choose that one. Right? I can choose any element of B. This one, maybe I'm going to choose, over here. This one, I'm going to choose this one again. And this one, also going to choose this one again. Here's. And this one, I'm going to choose, that. So, let's say to choose an A to B function, we get to independently choose I'll say the element of B corresponding to each element of A. Okay, so hence, by the product rule, right, the total number of ways to do that is just the product of all those choices. So I have, the number of choices for the first element of A. I have, whatever the size of B is, that's how many choices I have. I can choose any one of those elements of B to be output. Times, right, I have B choices for where to send the second element of A. Times B choices for where to send the third element of A, times B choices for the last. So the total, the number of these is the size of A. Right, so for each element of A, I get to make a choice of few things where to send it. This is just these, oops, size of e to the power of this size of n. There's actually a very interesting and deep connection between functions and exponentiation. This is just kind of scratching the surface, but at least we can see that the number of functions between two sets has to do with the exponent. So in other words, we could write it as the size of the set A, R, B equals this. Yeah, so we can see, well, if A and B are both bool, then it's 2 squared, which is 4. So that makes sense. But if I asked, for example, how about if I have a function from the set 1, 2, 3 to the set of booleans, the number of functions would be 2 to the third. Any questions about that? All right. Let's talk about, we'll call this subtraction rule. So as an example, just to illustrate what we're going to do, you want to order lunch. And restaurant A has 13 items on the menu. Restaurant B has 24 items on the menu. But sorry, wait. Okay, no, we're not doing the subtraction. We haven't done the addition rule. How can we use subtraction? Let's do addition first. Robust. How many different lunches do you have? I'm assuming that you just want a single item for lunch. It gets more interesting if you can like combine items, but I mean this is a pretty easy, pretty obvious to us, right? If I can order 13 items from here, I have 13 choices from restaurant A, or I have 24 choices from restaurant B, then obviously my total number of choices is just the sum of those 37. Okay. So 37 is the sum of the choices. In general, let's say, suppose choosing something means just the sum C1 plus C2. Okay. Another way we could say this, in other words, if I have two sets A and B that are disjoint, that means they share no elements in common. Or another way you could say that is their intersection is empty. Then the size of A union B is just the size of A plus the size of B. All right, but of course we know that's not true if they overlap. We'll think about what happens if they overlap in a little bit, but for now we'll just say, look, if we have a scenario where they don't overlap at all, then it's very easy, you just add them. You know, like in our, I guess it didn't say, we're just kind of assuming in this example with restaurants that, you know, they don't have any items in common. So, I want to come back to the example that we did at first about trees, about binary trees. Because we've actually now seen enough stuff that we can put together in order to figure out some things about trees. So, say we call counting binary trees. Okay, so for example, I'll say with so like we had 0 branch nodes, 0 branches. Right, there was a single binary tree which we just kind of knew as a dot that represented the leaf. If there was 1 branch, right, we just had this tree like this. Oops. Branches, oops, little dots for leaves. Right, we had this tree, or we had this tree. I'll just write one more. I think we'd gotten as far as listing all the trees with 3 branches, and I think we found there were 5, right? So let me just quickly draw them again, just to have it on the screen to talk about. There was that, and we could go this way. We could also have that balanced one that looks like this. And then we could have the mirror images of those ones at the beginning, so that one, and then we could have this one there. So there's 1, 1, 2, 5, and then a question mark. So let's think about this in terms of, you know, if I say, all right, I want to choose a tree with a certain number of branches. Like, how can I do that? How many ways do I have to choose a tree among all the possibilities? One thing we could notice is that kind of one of the first choices I could make is how many branches do I want to put on the left side, and how many branches do I want to put on the right side? So I always have to have a branch at the top. So if I kind of split these up, I can split these up like this. All right, so these ones have like 2 branches on the left and 0 on the right. Yeah, so like this tree, there's a branch at the top, and then on the right, I don't have any more branches, it's just a leaf. On the left, there's going to be 2 somewhere down there. And the same here, right? This is another tree with 2 to the left and 2 to the right. And then this one has, you know, 1 on each side. And and then these ones have 0 on the left and 2 on the right. Like blue dots here for branches. So, those are, they don't overlap at all, right? Like if I have a tree with, some number of like, 5 branches on the left and 3 on the right, and I have another one that has 4 branches on the left and 4 on the right, I know for sure those cannot be the same tree, right? So if I kind of think about splitting up all the trees according to how many branches they have on the left and the right, those do not overlap. Which means we can use this addition rule to say, well, if I could just count how many there are that have 2 on the left and 0 on the right, and then I can count how many there are that have 1 on the left and 1 on the right, and then I can count how many there are that have 0 on the left and 2 on the right, I can just add those up, and I'll get the right answer. Right? I mean, in this case, it's obvious. There's just 2 of these, 1 of these, 2 of these. But in general, we can count, according to how many branches are on the left and the right, and then add. And, well, okay, once I've committed to having a certain number of branches on the left and a certain number of branches on the right, how do I count how many of those there are? Well, let's think about, like, if I knew I had let's say I have a branch at the top, and then I want something with 3 branches over here, and let's say I wanted something with 2 branches over here. There's a lot of ways I could do that. Question is, how many total different ways can I choose some tree with 3 branches to go over here, and some tree with 2 branches to go over there? Well, the choices are independent, right? Which tree I choose to go over here has no bearing on which tree goes over here. They're completely independent of each other. So I can use the product rule. I can say, well, how many different trees are there with 3 branches? How many different trees are there with 2 branches? I can choose them independently, so I just can multiply those. That would give me the total. So we can choose the left. So here's an example. You can choose the left side and the right side independently. So the product rule applies. So I already know there's 5 trees with 3 branches, and there's 2 trees with 2 branches. So apparently, there are 10 trees that have 3 branches on the left and 2 on the right. Okay, so there's 5 times 2 equals 10 trees with 3 branches left and 2 branches right. Does this make sense so far? Any questions? So let's see if we can figure out, if we can calculate how many trees they're going to be with 4 branches. So let's And let's say, let Tn equal the number of trees with n branches. Okay, and the question is, what is T for? Well, remember, the first thing that we can say is, well, we'll have to have one branch at the top. And then we can decide how many to put on the left and how many to put on the right. So we could put 3 on the left and 0 on the right. In which case, according to this argument here, if I have 3 on the left and 0 on the right, I can just multiply how many of each of those there are to get the total. There's, 5 with 3 branches, and there's only 1 with no branches. So, but in general, it's going to be T3 times T0, right? This is the number with 3 on the left and 0 on the right. Plus, right, alternatively, I could put 2 branches on the left and 1 on the right. And that would be, right, how many ways can I choose, how many trees are there with 2 branches times how many trees are there with 1 branch. Right, or I could do T1 plus times T2, put 1 on the left, 2 on the right. Or finally, I could put 0 on the left and all 3 on the right. Right? That covers all the possibilities. And so that is equal to, well, what is this? T3 is 5. So 5 times 1 plus T2 is 2 times 1 plus 1 times 2 plus 1 times 5, which is equal to 5 plus 2 plus 2 plus 5, which is 14. I think we actually saw that number, like, Disco calculated that number for us. We were able to calculate it ourselves without actually listing all the trees. Let's just do one more just for fun, or just to see how this works out. So for T5, it's going to be the same pattern, right? Except now, like I could start with putting 4 on the left and 0 on the right. And then it's going to go from there, right? So I can put 3 on the left and 1 on the right. Or I can put 2 on the left and 2 on the right, 1 and 3, or I could do 0 and 4, which is equal to, let's see, 14 times 1 plus T3 is 5 times also 1 plus 2 times 2. Plus 1 times 5 plus 1 times 14, which is equal to 14 plus 5. Well, it's really, I could like combine something. It's like there's 2 14s, and there's 2 5s, and then there's this 2 times 2, which is 4. So this is 28 plus 10 plus 4, which is 42. So we didn't exactly come up with like a formula for the number of trees. It turns out there is a way to come up with a nice formula. That would take us farther afield, but at least we came up with kind of a procedure for calculating. If we know all the numbers, up to a certain thing, we can find out the next one by kind of doing this procedure, which is a little bit tedious, but it's still way less tedious than actually trying to list all 42 trees and convincing ourselves that we got them all. So by the way, this sequence of numbers, so we had 1, 1, and then 2, quite as famous as the Fibonacci numbers, but, close. You can look them up if you want to know more, but they show up in all sorts of places, just like the Fibonacci numbers. Okay, so actually, let's finish up by talking about the subtraction rule that I tried to talk about earlier. And it's very simple. It's just like if we're doing the addition rule, but there's some overlap, what do we do? So, you know, for example, right, you have the same restaurants as before, right, with, I forget how many items they have, like 13 and 24 items, respectively, I think. But 9 items are the same. You know, like you could get a hamburger from either restaurant, and the restaurants aren't so different that like you really care whether you get a hamburger from one place or a hamburger from the other. It's kind of like it's a hamburger to you. So the question is now, how many choices do you have? Well, do something. What do you think? How many total choices do I have for lunch? If I don't care, like getting a hamburger from one place or the other, I don't consider that a different lunch option. It's just a hamburger. Okay.
13 plus 24 minus 9.
Why?
Because essentially, like, if you know, just adding them up together completely, they're going to be 9 overlaps.
Right.
So we're moving one copy.
Exactly. Yeah, that's the way to think of this, right? And we saw this before, right? This is really, in disguise, in the sense of this formula that we came up with before. Like in general, if you have A union B, and you look at the size, right? They could overlap. And so if we just add the size of A plus the size of B, that might be too big, because we maybe have counted that overlap twice. So we just have to subtract the size of the overlap. Okay. So if we want to write it out, let's say, you know, if choosing something means making either one choice in C1 ways or another choice in C2 ways, but the choices overlap. Then the total number of choices is C1 plus C2 minus the number of choices in common. Okay, and let's just quickly do one slightly less trivial example. The restaurant example is kind of obvious. How many strings of 8 bits either start with 1 or end with 0, 0? Okay, so I want to count, you know, strings of 8 bits like 1, 0, 0, 1, 0, whatever. But I want them to either start with a 1 or end with a 0, 0. Well, first we can answer the question, you know, how many start with 1? So what would you say? How many strings of 8 bits start with a 1? what I have to choose. Kathy?
It'd be 2 to the 7th.
Why 2 to the 7th?
Because there's 7, we know that one of the bits is 1, so there's 7 different things.
Yeah, that's right. So, yeah, that's a good way to think of it. The first one is 1, so I don't get to choose that at all. I kind of ignore that and say, well, what I have left to choose is, what are the other 7 bits going to be? And I have 2 choices for each, they're all independent. Right, so, 2 to the 7th. Okay, how many end with 0? With 0, 0? So similar argument, right? If it has to end with 0, 0, that's fixed, and I have 6 bits that I can choose, so 2 to the 6th. Okay, so I might think at this point, oh, I can just add these, right? Because either it's going to start with a 1, or it's going to end with 0, 0. Okay, but do they overlap? Yes, they do, because there's some bit strings that both start with a 1 and end with 0, 0. So, how many are there? How many start with 1 and end with 0, 0? Well, the first one is fixed, the last 2 are fixed. What do I have to choose? I just get 5 bits in the middle that I get to choose, right? So that's 2 to the 5th. So now I can use the subtraction rule and say, okay, well, the total number, so the total is 2 to the 7th plus 2 to the 6th, but that's overcounting, so I need to subtract off the overlap. That's it. I think this is equal to 160. You can check that, but whatever that is. Okay. So there will be a new module coming out very soon on some of this counting stuff. I will